where we left out yesterday, 215. I was talking about graph embedding, and that's a very important notion you will see useful in many applications. So your typical, the problem is the following: we have a graph, and you would like to represent it with data. So each node would have a vector associated with it. And actually, this graph itself can be available right away from it's the original data you have, or it could be also constructed. So again, the original graph is here, and you want to get for each vertex a vector that represents it. This could be useful as an example. We talked last time about visualizing a graph, right? You have a graph that's given to you, and you would like to represent it in 2D. So each point will have a coordinate now in 2D, and then you add in this connection, and you have the visualization of your graph. I'll show you an example in a second. So vertex embedding, you map every vertex to a node, to a vector in RD. So this is used in many applications. The graph itself could be obtained from a similarity graph. We talked about that earlier. Okay, so now here's a representation of what I want to do. I get some data. I get a similarity graph from it, like here, and then I would like to project the data to RD in such a way that this representation is somewhat faithful of the graph I have here. So there are many methods that do this. Some of the classical ones are eigenmaps and LLE, and I'll talk about those now. So in eigenmaps, you use the graph Laplacian of your graph. So this is just a reminder of what that is. So once you have that graph, you would like to do this embedding so as to preserve something. In this case, here's what you would like to do. Remember that property we saw a while ago on this thing. I'm just going to show you that we had this thing before. The trace of y and y transpose is half of the sum of wij's times the distances between yi and yj squared. So that is a very important property that we'll now exploit here. So I would like to get the mapping in such a way that when I have something in here, when you have yxi close to xj in this graph, the yi is the dimensional one, is a low dimensional representation. That is also close to yj. So I'd like to do the mapping in such a way that these distances essentially are preserved. So that means that I have to minimize this, right? So when xi and xj is small, this also has to be small. So when wij exists, when it's non-zero, this has to be small essentially. That's the argument. And then it's not very difficult to solve this problem. And there is a constraint in here, and then there's some arguments of why that's a good constraint. By the way, remember that y is a flat matrix. So if for each column is a representation, each column of y, the matrix y is a representation of one item xj. So this is the yj we were talking about. Okay, so this is the problem you reach, and then you solve the problem. You essentially get again an eigenvalue problem, and the components transpose will give you the vectors transpose will give you exactly the vector yi you need. That's all. The next method, it's along the same lines, is called LLE, locally linear embeddings. So it's very similar to eigenmaps. It's almost the same, except in the way you define the graph. Okay, in eigenmaps, you define the graph from similarity. You have a similarity graph, and then you get the Laplacian from it. Here, what you do is a very simple idea. You have your original data, and you construct wij's in such a way that xi is it's a sort of convex combination of its neighbors as best as possible. So it's not very, it looks like an expensive thing to do. It's not too bad. It's a localized problem. It's a small least squares problem you have to solve to get the combination. So that's, once you have that, you have this big matrix W, and then you would do exactly the same thing we did with eigenmaps. Okay, so it gives you again an eigenvalue problem. This time it's actually more of a singular value problem than an eigenvalue problem, and this is the second method. Okay, and there are many, many other methods. Now, but the problem with these types of methods is the following. If I have to use this for something like classification, so if it's okay to get data from data in Rn to Rd. I can do it once and that's fine. But now if I have a new data item and I would like to say if it's close to something or trying to classify it or something, then this would not be easy because every time you'd have to do that, you'd have to solve this big eigenvalue problem. And so the matrix changes, everything changes. So it's not very practical. So this is called the out of sample problem. So your out of sample extension problem. So you come across this difference between the explicit mapping and the implicit mapping. What I described to you now, these two methods are implicit in the sense that you just get from the original data to the last one, but there's no explicit mapping like this phi here that you can just apply. So in the explicit methods, you actually get something like this, for example. This would be your the column xi, and this would be your, or xi, there would be yi here. And the yi is obtained by simply applying V transpose, so V transpose. And the goal now is to find this V, right? So there are methods that do this, and then there's yeah, this one is called the locally preserving projections, which again leads to an eigenvalue problem. It's not very different from what I just described. They all use this property here, right? They all use this property, minimizing this property here, minimizing the trace of y ly transpose in some way. I'm sorry. Yeah. Okay. So I'm moving a little too much between workspaces. Sorry about that. So now there's a method called LTP, and we have developed another method a while ago, which uses an orthogonal projection instead of just standard projection, which was called ONPP. I'm going to just very briefly mention that this is based on LLE, and the rest is very similar. And now there are a lot of methods that have been looked at recently. So this work that I just mentioned is from the about 15 years ago or so. But there's still interest in these things, of course. It's very, very fundamental tool. And there's some of the references are here. There is one particular thing I want to mention, and there's a viewpoint now that has changed a little bit. So you're trying to find what is called the graph factorization. So instead of doing what we did before, just to try to look at the trace, now I want to get to vectors yi such that wij is close to yi transpose yj. So essentially, we're trying to minimize something like this, for which norm of this. So it's a graph factorization, right? Yeah. Interesting viewpoint. So what I just described, these two methods of LLE and eigenmaps can be viewed as dimensional reduction techniques, because you're starting from data in Rm, then you get a graph, and then you get the data from it. You get the data in Rd from it. So you go from Rm to Rd, right? So you can view that as dimensional reduction, one form of dimensional reduction. The dimensional reduction here aims at preserving some essentially similarities or whatever. Okay. So this is generally what we do. And then I talked about linear and implicit mappings. So standard explicit or implicit mappings. This is what I just talked about that. Now, one of the basic tools in this whole area is PCA. So it's a dimension reduction now more generally. You don't have necessarily a graph in between. So you got data, and you would like to find low dimensional data, yi, that approximates the high dimensional data xi, and that the principle here is trying to maximize variance of the projected data. And I think everybody knows about this method, more or less. It's really, I think, quite straightforward. I mean, quite common. So I'll just skip that. Now I'm going to talk about unsupervised learning in general. So this is clustering in particular. So you have data, and you would like to cluster it in this way. All right. For example, you have these are digits that are clustered. These are materials that are clustered, etc. So here is a simple example. I was going to give a demo with this, but I think I'll skip that. These are digits, and you can now try to project that in 2D to visualize this and see, for example, this PCA gives you this. So if these are numbers between 1, 0, and 4, so five digits, and you see that, for example, 1 is pretty nicely separated from the rest, and so on. This is LLE, this is kernel PCA. I didn't talk about that. So it's PCA with essentially changing the inner product to make it something nonlinear. And then this is our PP. Okay. So one illustration about all this of these dimension reduction methods is this dimension, the representation of the graph. Remember when I showed you this thing, right? I think it's not demo. March. I think I showed you this earlier. Oh wait. Okay. Okay, let's try it again. Okay, so now you see here's the matrix and then the graph. This was, remember, this was a triangular grid, random walk on a triangular grid, and MATLAB did a wonderful job at figuring out that it was actually a triangle behind the scenes. So I have something which tries to do something similar with very simple tools that are available here. So test mark. Okay, here we go. So what I do is get my Laplacian, get the eigenvalues, and then look at the first two eigenvectors and do a plot of the matrix A with the coordinates x are given by x1. So you give, if you gplot plots a graph, it's not the same as the plot function of graph. So given coordinates, it points, it will plot the links. So you have to give it coordinates and the matrix. And then now this is eigenmaps with 14. So eigenmap constructs a nearest neighbor graph, similarity graph, okay? So you have to give it the number of neighbors. In this case, I think 14. And I just give it a dimension, here just 2, dimension, the number of vectors. But this is the number of coordinates I need. But this is the dimension of my y, the number of components in y. And then I plot, again, L with these V's. The graph with so let's try that. And right here. Okay. So this one, the first one here is simply eigenvectors, the first two eigenvectors, lowest eigenvectors of the graph Laplacian. And the second one is the one given by the eigenmaps. I think I should remove that. I'll see that right here. Not as nice as what you get from MATLAB, but I would sometime look into what MATLAB did to get that. All right. Any questions about this? Okay. So now I think I will just, the next topic that I wanted to discuss is spectral densities, eigen count and so on. But I really will have to skip big part of this one. I'm just giving you the main ideas here. So the problem that we face when the dimensional reduction techniques and many other problems, I had a question yesterday about this, is how do you get this K? How do you figure out that K? What dimension should I use? Okay, so often this is done in ad hoc fashion. So really the actual optimal K is the intrinsic range of data. So you have your data, you have maybe 10 singular vectors that matter, the rest is garbage, it's just noise. So there are two scenarios. One is when you have the magnitude of the noise, then you say, well, I just essentially ignore singular values below that threshold. And then the second scenario is when you have no idea. This is somewhat similar to what Jim was talking about last time. You have these two scenarios, right? So in this case, you have to figure that out. So spectral densities will allow you to do this part specifically. So I'm going to go now to page 51. So in spectral densities, I'll just give you a brief overview of this thing. There's a lot of stuff that that's required to go through all this. I'm going to be very brief. So the spectral density or density of states, as it's called in physics, is a function that provides some sort of global view of the spectrum. So essentially, what you get is a probability distribution for having eigenvalues at any given point on the interval. So that's very important because you can have essentially, if you can construct that very quickly, then you have a good view of the spectrum. And these tools that have been developed are very cheap. Okay, so let me just go a little bit more about the spectral density. The definition is here. And you can see it's totally useless as a formal definition. Density of states is the sort of average of these Dirac distributions at each lambda I. So this is not a function even, it's a distribution. And you can think of it as a very, very discontinuous kind of function, this phi of t, right? But so the way it is given here is not very useful because the eigenvalues are not known, for one thing. You don't want to compute those. But what you do is you actually replace the distribution by, oops, sorry about that, by an approximation like what you have here. Oops, I lost the thing. Try again. All right, so this is now each of these delta i's is replaced by a little Gaussian, and you can select the width of the Gaussian, depending on smoothness you want, and several. So there's a number of ways of doing that. Once you do that, then you get the smooth function. Okay, but then again, this requires lambda j's, not very practical. What we do instead is essentially discretize your interval and put one of these at each of the discrete points you have, and then do a sort of probing. So you're essentially computing this at that point, the distribution around that point. And there are techniques that do this. So I will just go to just right here and show you one example only how this works. I actually also have a demo that shows this, but in the interest of time, I'll skip that. Here's a matrix coming from actually ages ago in our group. It's a benzene molecule, and we have this matrix that comes from electronic structure calculation. This one is very simple, very small. I have the same example with maybe 30,000, same molecule. And you could do that on this laptop in a fraction of a second. So here's the matrix, the pattern. This is the size, number of non-zero elements. And in 0.2 seconds on this laptop or standard kind of current processor, you get the distribution that you see here. So you get a very good picture of the spectrum very quickly. And you could do a couple of 100,000 by a couple of 100,000 again on a standard processor within a few, like 10 seconds or so. Not bad, So it's not the same as computing all the eigenvalues, but you can a pretty good picture of the spectrum. Okay. Questions about the spectral densities? So now, how do you do this? How do you use this? I think I'm going to go to 56. No, that's not what I want. I want to go to 266. Okay, so how do you do this? How do you use this? Here you go. So let's try to see how we do this for to determine the numerical rank or the approximate rank. So definition of the approximate rank is the one that's stated here. So R epsilon, given epsilon, R epsilon is simply the minimum of the rank of B with the restriction that the constraint that A minus B, the two norms A minus B less than or equal to epsilon. And if you work out the details with SVD, etc., it boils down to this definition here, which is a little simpler to understand. So R epsilon is exactly equal to the number of singular values that are larger than epsilon, larger or equal to epsilon. That's the definition. So I have to find, if I want to determine the relevant number of singular values, I have to find that epsilon. I have to say, well, where do I cut? So there's two different problems. As I just said, one of them is to get the good epsilon, okay? And the second one is to, once you have the epsilon, get the number of singular values larger than equal to epsilon without computing them, obviously. So there's two separate issues. So let's look at the first one. Here are three different distinct scenarios you could have for, where you have a very sharp decline. This is almost an exact K rank matrix. This one is a more typical scenario, all right? And these are, what you see here is this spectral density is computed with some method called kernel polynomial, the kernel polynomial method here. As you can see that really you have a sharp drop in here, somewhat a sharp drop, and then some oscillations here. And then this one is not very clear cut. You don't have really something that comes back up. This is very common also, right? So you can see from here that one way to get a good idea of this epsilon is just to try to identify where this thing goes back up. And you just look at the function and see where the derivatives become equal to 0. And the function is available to you. It's explicitly available. Okay. And this one as well, that tells you that you have to be careful. It will not necessarily go back up, but at some point it will just wither down. It will be, so there you have to take care of this case. You have to be a little more careful. But these are fairly easy, right? So essentially we do something like this. You identify epsilon as the minimum value where the derivative starts to be larger than a certain tolerance. It goes down very fast, and then in absolute value, of course, and then at some point it starts to be larger than epsilon. And then that's how we select your epsilon. Okay, and then once you have that, then the second problem is to get the number of eigenvalues. That's really just integrating the spectral density, integrated between 0 and epsilon, right? That's the opposite actually. The 0 epsilon will give you the null space, so the epsilon to the largest one. Okay, so here's an example we run. This is this matrix that is from, again, the Swiss sparse collection. Thanks. And then you can see here, it's actually very sharp in this case. And then, by the way, I should also mention that these methods, all one way or another, these spectral densities or density of states, they all one way or another exploit trace estimation. We have this presentation, Alice got to know this a few days ago. They all use that technique. Okay, so you see here, you get the rank. This is where you see the red line. The dashed line here is exact rank. And this one is the accumulated, this is the sort of mean or something like that. So at the end, you get something that's very close. This is the estimation to the rank. It's very close at the end when the number of vectors you use. So this, okay. So these are essentially, this is done by long shots. You run long shots every time. You have 30 vectors, you read 30 times, and you have some sort of linear average, and you get something like this. Okay, good enough. So next, I will talk about the T74 here, supervised learning. So I mentioned a little bit of this earlier. We have data that's now labeled. And for example, you can say span, non-span, malignant, non-malignant. And then you have these other things where you have several classes, photovoltaic, hard, semiconductor, conductor, whatever. And then you have digit recognition. We have the numbers, digits from 0 to 9. These are a few examples. And now you're given one item and you'd like to place it in one of these classes. So a class is simply a set of items that have the same label. So how do you do that? And if you do, again, if you do something like LRE or eigenmap, this is not very practical because this mapping is not explicit. But if you do, there are methods like PCA, for example. This is not too bad. You have your V, the transpose times. So essentially, what you do is do the comparison in low dimensional space. This is what you have here. So these are, for example, the case of digit. I had a demo with this, but I will skip that. So you have digits that are images, so those are pixels, and you vectorize them and have vectors. This could be a long vector if you have 16 by 16, will give you 256. So it's really it's small. When you have 100 by 100, you already get 1,000, 1,000. So once you have those, then what you do is the first thing you do is you do the dimensional reduction. All right. Now we have, and that means you have this with explicit mapping. So you know how to map this to this one explicitly. With, for example, the easiest case would be PCA, right, or the SVD. So now each of these will have a representation here, okay? And now you're given a digit which is not in here, and you project it the same way as you did the other ones, with the same mapping V. And now you could do the comparison, really using anything you want, distance or whatever. I need the comparison. So that's how you could do it. And some of these simple techniques that have been developed do a pretty good job at this. Although now I think people will use other techniques. But so this is a very simple illustration of what supervised learning does. Okay. So the basic method in this context is the k nearest neighbors classification. So it's a really basic. So you take you have data around your test item, which is this one, which you don't know how to label. And then you get the closest, the k closest ones from it. And then you use the idea of a vote, right? So the largest number, the class that is the most represented in this ball or the circle would be the class you assign to your unclassified item. This is the technique. So now we're talking about linear classifiers. So you have a hyperspace plane that separates two items. In this, here is a case that is not so obvious, and you could use kernels. So kernels are extremely powerful, and they have been used a lot to essentially change what it is simply changing the inner product. Okay. So by changing the inner product, I mean, instead of having this usual inner product in Rn, we have a sort of nonlinear mapping that gives you that. So K of X and Y will be your inner product. And there's a lot of justifications. You're going in higher dimensional space and so on. But you see here, for example, this kernel, which is just a standard Gaussian, will tend to squeeze items together. It will be very close to each other. Now you can separate this a lot more easily. Sorry about that. Yeah. You see, you can. This is very easy separable, whereas here you could not do that easily. This is a separation you get from using standard bisection technique. Okay, so these are simple linear classifiers are based on, again, hyperplanes. So you select a certain vector u, and when you transpose xi is positive, it's one class. When it's negative, it's the other class. So that's quite straightforward. Method in this category is the Fisher linear discriminant analysis, which is an old method used for a lot of different things. So this one uses the labels to build a good projector. Okay, one that can discriminate well between classes. So how do you do that? You define between scatter, which is a measure of how well separated distant classes are, and you define within scatter to see how a measure of how well clustered the items within the same class are. And then you would like to define a projector that does the following. You would like to maximize, you'd like this to be large. Classes have to be well separated. And within the class, you would like the items to be well, nicely close to each other. So clustered within each other. Okay. So, and then you define this, to do that, you define these two matrices. The mu k's are the centroids of each class. Okay. And here are definitions. The mu is the mean of the whole set. Mu k's are the means for each class. Xk is the kth class, and Ak is the size of Xk. And then the idea is you would like these to be well separated, so the mu i's have to be more or less far from each other. But you also within each of these, you like the xi's to be well close to each other. And then you look at these two inner products, and the idea is that you maximize this ratio. So this is to find one hyperplane, right? A is one-dimensional in this case. So you can find easily one hyperplane by maximizing the ratio of the in-between scatter over the within scatter. So that tends to give you a large one here and a small one here. Okay. And of course, you can, one-dimensional is not good. You could generalize that to arbitrary dimensions. That gives you now a trace instead of having just one vector. So this is LDA. Okay. Support vector machines work in a sort of a similar way. The ideas are somewhat similar. Like you're looking for hyperplanes that do dust separation, that you don't have these classes. So here is, in this case, we're looking at just two classes essentially. The hyperplane that separates you two. And this is your, the hyperplane. And the classifier will be the sign of this, sign of W transpose could be. So if it's positive, it's one class. If it's negative, it's the other class. So instead of doing it this way, we just, instead of saying positive and negative, we'll say larger than 1 or less than -1. And that gives you, it's a sort of form of normalization that helps with the, it simplifies a little bit the notation. So in that case, the constraint will become this. So if it's positive, if it's larger than 1, if it's negative, this would be larger than 1. If it's positive, it would be, so yi would be either +1 or -1. Then because of what you decided here, that's the constraint you have to have. And therefore, what you'd like to do now is to find a sort of hyperplane. This actually hyperplane that we're looking at is somewhere in the middle. We're representing these two. They're called the support hyperplanes, and you want to maximize this margin gamma in between the two. And it turns out that because of the notation that I just talked about, that this gamma is equal to do divided by a norm of W, W being this vector here that's used for that. That's not very difficult to see. And you come up in the end with this problem. So that's what you have to solve. Minimize the norm of W squared subject to this constraint, which we just talked about. So that's the constraint, and you could solve the dual problem, which is a little bit more convenient in this case. So there are a couple of modifications. The one that I want to emphasize is that this is totally useless without kernels, because you can, as we saw, it's not easy to separate data that's not nicely separable by planes. So you have to use kernels. And that's these are the two main ingredients. There's some modification in here. And SVM used to be very, very popular. It's still popular now, by the way, but it's not as, it has been a little bit displaced by the neural networks. So this one, so neural networks, it has been talked about quite a bit. So I will skip this just to mention very briefly one viewpoint of the problem. The problem is you have your initial data here, and you have your target data here. So these are for some xi, you have some values. For example, it could be just spam, non-spam, or something like that. And you would like there's a function that takes you from the label, this data here, to this each of these yi's. But that function is defined through several stages. That's the definition of this function. It's defined through several stages. And the question is, how do you minimize this? So how do you make this function phi that you're looking for very close to, as close as possible to the y that's given here? Okay, and then by optimizing the parameters in each of these little stages. And that's essentially what the function, this is exactly what you do. You have this function is defined this way. And you'd like to minimize some objective function at the end. There are a couple of ways you define it. So this was discussed in detail by Jay and others yesterday and 2 days ago. So I'm going to skip that and go to 294. So it's right here, graph coarsening. So this is the last topic. Well, yeah, the last topic that I will cover, and I will cover it a little briefly, but graph coarsening is a very important tool, both in scientific computing, and now it's just starting to be also discovered, but not discovered, but utilized in machine learning. So the goal of graph coarsening is the following: given a graph, find a coarser, a smaller graph, which has fewer vertices, fewer edges, obviously, which is a faithful representation of G, the original graph in some sense. Okay, so this illustration here. So for example, these two will give you a node here, etc. So in scientific computing, you would like to exploit the this coarse representation in something like, when you solve linear systems or whatever, with eigenvalue problems also, and so on. So the big success story in scientific computing is obviously multigrid and AMG, algebraic multigrid. So here we have data. So we have a node here. You have neighbors. These are the AIJs in your system. You decide on depending on what is called strength of coupling. You decide of neighbors that you select as coarse set. So this would be your next level. Okay, and then you build different things from this. When you have your once you have your mapping, this is actually the mapping that I was talking about. Is You have this restriction, prolongation operators that come from going from the fine to the coarse and backwards. And then you come up with the linear systems that are smaller, and they can repeat the process. I'm going to skip that and show you just one thing you can do with this sort of things here. Here's a very simple illustration here. And I'm going to just, without too much detail, give you what I'm doing. So this is a linear system. Actually, it's one of those, again, one of those that comes from the, you can find this matrix. It has been contributed many years ago. It's in CFD. And the size of this matrix, well, it's like 19,000 or something, yeah. So here is the first level. And then whatever is left, you do, this is the course, so this is the course graph, the course version of the original problem. And then whatever you do a second coarsening, etc. And then in the end, what I do is simply this, take this as ordering. You don't have to modify the matrix and do an ILUT on it. So the coarsening here is used only to find an ordering. And then you do an ILUT on it, and you can, the performance is not pretty good for this example and the other ones. This is really, what you see here is the amount of fill you need. And this is using a very, very simple technique based on SOR, but using this ordering again, whereas this one is using the original ordering. And how do you come up with this? Well, details are here. It's a little bit complicated, but this is, you have to define a way of traversing a graph for coarsening. So a lot of the methods that are based on coarsening rely on an ordering for traversing the graph, an order in which you traverse the graph, which in fact in which you traverse the edges specifically. And in particular, for example, for multigrid, that's adapted. You do first do a selection, and then you adapt that order and you continue. It's a little complicated. So I'm going to talk a little bit about that actually now. So how do you coarsen the graphs? So the one of the most common approaches in this context is called pairwise aggregation or matching. So maximal matching, or there's a couple of terms that are used. Strategy is simply this: you take two nodes that are, you find them to be somewhat related, or there's a strong connection between them, and you collapse them into one node, or one of them will represent the two. That's easy enough. Okay, and that's done by traversing the edges and then saying, now this is in a certain order. That order is very, very important. And then you say, well, this is, let's put this together, the next pair together, etc. Okay. So that's essentially described here. For each node I, you build a set Si of nodes that are strongly connected to I. You traverse the graph. This is taken from whatever is done in actually AMG. You traverse the graph in a certain order of preference. Next unmarked node in this order, say J, is selected as a coarse node. And then the priority measure to selecting for traversing graph is modified. That's a little complicated to do. So some of the simpler versions, we don't do that actually. We just do it at the beginning. So the heavy edge matching just matches a node with its largest off-diagonal neighbor. That's all. So I'm going to show you a little thing that does exactly this. All right, so I'm going to do here. So by the way, I want to make sure to mention this. I realized after I posted these MATLAB scripts that many of them are not quite the latest ones I'm using. There's some things I'm missing. As you saw, there was a couple of times where I had forgot to change something. So I will repost them afterwards. I will post exactly what I showed you, so you can try them. You can I use that in a course. So later on, I will also use these in that course, and you can access these MATLAB scripts and many more actually. So, MTest course, right, here we go. So I create a graph. That's a simple thing, very similar to the one I showed yesterday with finite element assembly. And I'll just show the graph here. And then I do multi-level coarsening. All right, and here's what happens here. I will show these matrices one by one, the levels one by one. So actually the number of levels is what here? I have levels, I think it was like 4 or 5. All right, I'll just do it. It's actually 4, right? You see it here. It's the number of levels. So let's do that. All right. This is the original graph. It's a big, it's an ellipsoid. I think it's circular. No, it's an ellipsoid, and you have a hole in the middle. Okay, and you do Delaunay to get the points, etc. So now let's look at the next level. Level 1. Here it is. Not very. It's very simple technique, by the way. So level 2. Level 2, level 3, level 4, and that's it, I think, right? Level 4. So that's what you get at the end. It's a very small representation, and it gives you a good idea of what was there in the beginning, right? So this could be useful for some situations. That's a much smaller graph than the original one. Okay, so this is heavy edge matching. Now, this is the details of the algorithm. I don't think that's useful. Now, what I will do is tell you briefly what other people have done, what has been done in the literature to coarsen the graph by other methods. Another technique that's been used is using independent sets. So an independent set is simply a set of vertices that are not connected by an equation. So if you think of the matrix, it's a set so that when you reorder the matrix to get that set comes first, that this matrix is diagonal. That's all. It's really a reordering matrix. You have a diagonal matrix. The 1-1 is the one as a 1-1 block. That's essentially what the independent set is. And of course, it's maximum in the sense you cannot add more points to it. You don't want to. It's not maximum in the sense of the largest one. It's just that you cannot augment it by other nodes. Okay. And then what you do is you define the coarse graph in this way. So you replace this. You have the Schur complement, but you replace this B by the diagonal. Okay, some diagonal, which is this one here. By diagonal, which is to say is essentially the row sums of A transpose. Okay, so that's one way. So what you could show easily is that the graph Laplacian SC is the graph Laplacian of the graph GC. So algebraic distance is another thing that has been used, and J.S. worked on this a while ago. It's really using what we know from convergence results of SOR type techniques or Gauss-Seidel or whatever. So the speed of convergence of these processes give you an idea of the algebraic distance between variables, and that could be used to essentially coarsen the graph. Okay. The next method that is really interesting, I found that to be fascinating. There's a paper in the 1930s, late 30s, by Cron, which does essentially use something similar to this independent sets, but they use actually full Schur complement. So this is actually in circuits. It's really an engineering problem. They want to get a small number of points to use to represent the original graph. Okay, and so what they do is they have this sort of splitting again in two. And in this case, what they do is they use the eigenvectors to get this independent set. It's not really an independent set anymore, but it's close, right? And then they use the Schur complement, the exact Schur complement, without no simplification in this case. So there are a number of arguments as how you could make sure that this is not too dense, etc. So we looked at this recently and found kind of interesting properties. So here's the independent set coarsening. These are some illustration of the graphs. In this case, in the crown coarsening, you use this reduced graph, the coarsened graph, and this one gives you just a simplified one like that. So these are just some questions related to this. Then they use specification. This is actually have been, there's a work by Schumann and al. That discusses this, and it has been really followed quite a bit recently. And so they deal with some of these questions that are here. Okay, so how do you use specification, for example? So specification is another thing which I haven't discussed, and it is another form of coarsening, but in this case, you don't reduce the number of vertices, you only reduce the number of edges. You make a graph sparser, it's the same origin, same number of vertices initially. So here's an interesting thing I wanted to show. I think you remember this example, right? I showed you graph partitioning with one eigenvector, right? It was not quite this one, it was very similar. Maybe half, was a half circle or something. And this is using the largest eigenvector. And you essentially look at the sign and assign one class to one to the other one to the other class. And here, what you get if you use this, this is using the smallest one. Okay. Sorry, the opposite. So this was the spectral graph partition. This one using the Fiedler vector, the second smallest eigenvector, right? And this one is using the largest one. The largest one corresponds to lots of oscillations. Okay, so what you have is, it's very interesting to see this. I don't know whether I can, yeah, it's not really easy to pull this in, but you see here, the details is that you tend to have nodes of different signs a lot more often than here. That's exactly what you want. So that's what's used in the crown coarsening. So I think I am basically actually not too bad. I'm reaching here. I wanted just to say very briefly here. So we did use this multi-level coarsening for computing the SVD. This is work I've done with former student Shashanka. So we looked at these ways of doing using hypergraph coarsening for SVD. And there's some results you could do. You could use actually this, we use this as an alternative to randomization. So why coarsening gives you something a little better than randomization because you use more information, right? So, and there are some results like these that are close to what you find in randomization techniques. So to really finish up quickly here, I just say that some recent work that has been done where coarsening has been used. This is HARP and MILE. These are two methods that have been used in the context of neural networks. So, you coarsen a few levels, and then you define an embedding, one embedding at the lowest level, and then you go back up. So you go back up to find the embedding of the higher level. So the idea is to find an embedding, right? And again, graph embedding exactly similar to what we have seen earlier. But this is done by using multi-level technique. So you do graph coarsening, and then every time you go back up, you update you refine your embedding to get a new one for this level, and you continue that way. All right. And then there's this other one here, which is somewhat similar. The main differences in the refinement. So I'm going to skip this part here. You see, eigenvectors have been also used for refinement, and in particular, leverage scores can be used. And we used that in our some recent work. I think I am going to give a few minutes here, so I'm going to stop with this, and you can give you some final words. Okay, so there are a lot of interesting matrix problems that arise now in numerical linear algebra on the effective use, effective exploitation of data. The one difference with Forsyth's time, I remember that quote from Forsyth, is that things happen extremely fast now. You do something and it's outdated within a year, something else happens that's much more powerful, or it could, there's so much going on, then there's actually, you run the risk of getting something that has been done already. It's very difficult to navigate in all of this. So it's a little bit overwhelming, okay? There are many resources available. There is huge potential to make good contribution, but I just mentioned there's a couple of challenges. There's a lot of changes, a lot of things, and a lot of contributions from a lot of different places. There's also change in culture when you go from mathematical kind of viewpoint to computer science or engineering viewpoint. So these are all challenges you can face. And I'll leave you with this quote from one of my favorite quotes from Alexander Graham Bell, who said the following: when one door closes, another opens, but we often look so long and so regretfully upon the closed door that we do not see the one which has opened for us. Okay, so again, I will update the material, at least the MATLAB part, and then there are a number of things that are available in my website. You could, if you're interested, you can visit that. In particular, next spring, I'm teaching this class, an extended version of this class.